So quick review of what we did yesterday, looking at the CPU that we built. Let's just walk it through. So here's the CPU picture, and we went through in the order that the instruction marches through the logic. So next BC logic, instruction fetch, decode, register file read, arithmetic logic unit, register file write, and then we added branches. So looking at that in the code, right, we have our PC logic, which is a mux, selecting the next PC, either increment by one instruction or taken branch. We have the instruction memory, which we instantiated at the bottom, and this hooks up the instruction memory interface signals to our signals, where the PC is driving the address that we want to fetch from, and then the instruction comes back from the instruction memory, and we call it inster, and that goes off to the decode logic. Then we created the decode logic to decode first the instruction type. So is this an I-type instruction, R-type, S-type, U-type, B-type, J-type, based on the opcode bits. Then we pulled the appropriate bits based on the instruction type from the instruction to form a 32-bit immediate value. Then we pulled out the other fields, which are all in a fixed position. Some instruction types support the field, some instruction types don't, so we condition those fields with a when condition. There are other places we could have used when conditions here. You're welcome to kind of look over your logic and apply more when conditions. You know, the when conditions are never necessary. They're just additional support as far as your the implied logic. They're not implying any combinational logic. They're just conveying information. As far as the flip-flops, they may imply clock gating and save power. Then we decoded down to the individual instructions. We decoded the branches and add and add I. We'll go back today, maybe today, and complete all of the instructions. We hooked up the register file, first doing read. So the decode logic has extracted the register indices for us. We hook those up to the register file, enabled by whether those fields are valid, and we hook up the data coming out of the register file to names that are appropriate to the CPU, source 1 value, source 2 value. We added support for branches to compute the branch target as the current PC offset by the immediate value. We determine whether, so that's here, we determine whether the branch is, whether we have a branch and it is taken based on the different branch conditions, evaluating those conditions. We hooked up the arithmetic logic unit, taking the values from the register file and operating on them depending on the instruction. And then we hooked up the register file write inputs. So we want to write the register file with the result from the arithmetic logic unit if the instruction has a destination register. We also excluded the write for register index 0, which is a special register which should not be written, always has a 0 value. All right, and at this point, we have the CPU completely capable of executing our test program. Today we're going to be looking at pipelining. So our CPU right now is trying to do all of this in a single cycle. That limits our cycle time, forces us to run on a slow clock. It's not going to be a very performant design doing one instruction per slow clock. So how do we get more performance out of our CPU? We'll do that through pipelining. All right, so into the slides. So before we sort of do that at the code level, we're going to have more fun with our cards. So what we need to collect up, and for folks online, obviously you don't have the physical toys to play with. Again, This is kind of an auxiliary exercise. It's not going to impede your ability to make forward progress on the remainder, so you can just sort of watch around the classroom and enjoy the chaos of everybody pretending to be CPUs. So, okay, I'm way behind here. So this is where we left off, creating the test bench. Hopefully at this point, your CPU reports that it passes. It produces a value of 45. So prep for this, you'll need your instruction memory card. Now you'll need all the individual instruction cards. Hopefully they're organized enough that this doesn't create a mess. You're going to need your register file card, something to write with, and something to indicate the program counter. Also, for this exercise, we're going to need some desk space. So you close your laptops. You can work on top of the laptops probably. There are a couple free tables here. Feel free to kind of shift your group to those tables. We're going to want to work in groups of ideally 4. I would say 4 or 5. Many of the tables are already 4. If you're in a table of 2 or 3, grouped together, you can be a table of 5. So 4 or 5, probably 4 is best. So this one's a team exercise, so it's just one set of resources for the whole team. Okay, so for this exercise, each of you is a different stage in the pipeline. All right. So the first stage in the pipeline is the next PC and fetch will combine together. So for that stage, you'll update your PC token to point to the next instruction, initially pointing to 0. There's going to be our clock is going to be a 6-second clock. So for each stage, do what you do in that stage, and then wait for the clock, and then hand off the results of what you do to the next stage. So PC and fetch, you're going to update the PC token and fetch the instruction, right? So you've got individual instruction cards. Fetch the instruction just means grab the right one at the PC. The next stage is decode, so you can decide amongst yourselves who's going to be what stage. The decode stage, we're not going to do the actual work of decoding. We'll take the shortcut and just flip the card. So for the decode stage, flip the instruction card over to show the human readable form of it. And then decode hands off to register file read. We're going to have the same person be decode and register file read. As we learned in RISC-V, there's actually no decode required to initiate the register file read, so they kind of happen in parallel. So you'll flip the card, you'll get the indices that you need to access from the register file, and look them up. So you'll just do this mentally. You have the indices, look up the values, just mentally know what these values are, and then you're going to hand those off after 6 seconds to the execution stage, which means, hey, execution, you're doing, so you're also going to tell the operation that's being done, right? So you say, hey, execute add of, you've read the register file, so add a value of 6 to a value of 2. Execute, again, just mentally, perform that calculation. After 6 seconds, tell the register file to write the value that you computed, and also you need to convey the destination register. So strictly speaking, the decode and register file read, decode specifically, should convey to the execution unit what is the destination register as well. So I guess it would be add 4 plus 8 and write it to this register, and then 6 seconds later, execution has done the computation, you have a result. You say to the register file write, write a value of 10 to register 6. Right? Register file write, we'll take the pencil, update the register value, and that's the instructions complete, right? So I guess ideally register file write, sort of wait 6 seconds and then update the value. And then repeat. So first we're going to do this sequentially. Do the PC, the PC and fetch person will do that operation, hand off the result, then decode will do their thing, then execute will do their thing, register write will do their thing, and then we're back to next PC and fetch. You'll do the next instruction. And line yourselves up so you're going around the table. Yeah, each of you is a single pipeline stage, single step. That's right. Each person is one of these bullets. So decide who you are. Well, if Professor Bofu wants to jump in with you, you can just be fetch. So I'll have each table be your own clock. So somehow we got a table of 5. So the table of 5 in the back, you can break up. I would say you can break up next PC and fetch into 2 stages. Right. Everybody else is 4. Okay, so everybody can be their own clock. Whoever is doing next PC can also be the clock. So whoever's next PC, count to 6 and, just say clock or whatever. All right, so whenever you're comfortable, whenever you're all set up, you can get started. Just walk through it. You've got your program set up. Just go as far through your program as you can. So it looks like the instruction cards aren't exactly as I was expecting. So they're intended to have the binary on one side and the decoded instruction on the other side. We don't have the binary. It doesn't really matter that we don't have the binary. It's not like it makes any sense to us anyway. So you can just start with the card flipped to the blank side, right? You don't know what the instruction is. You grab it. Once you decode it, you flip it over, you see, okay, that's what the instruction is, right? So let me just step this through one more time for everybody, right? So whoever is next PC is going to determine the right program counter to execute next. Let's say this is my program counter. It's pointing here. So first instruction we execute, I'll update the PC to 0. I'll fetch the instruction. So initially, you can have your instructions all upside down. We don't know what they are. We haven't figured that out. You fetch. You hand that off to decode. Now I'm decode. I'm going to flip the card, figure out what the instruction is. I'm also going to read the register file. So I have add with sources x0 and x0. I look at my register file card. Those are 0. So I tell execute now at the clock. I say perform an add of 0 and 0 and write the result to x4. Execute will mentally do the math. 0 plus 0. That's 0. And then at the clock, execute will tell register file write to write a value of 0 to x4. Register file write then, after 6 seconds, we'll update the register file card to put a 0 in x4. Okay? And then back to next PC. So next PC then would increment the PC, and the process repeats. And also replace the instruction card back in the instruction memory. So however far you got is fine. We had some overclocking going on. We had some seg faults. Things happen. So the next exercise is to run faster. Okay, each of you is doing your own thing. When you're running in serial, you do something, you wait for a while. We want to take advantage of the fact that you each operate independent of the other and overlap execution. So we're going to pipeline the execution. So you're doing the same thing that you did before, but you know the next PC is going to operate every cycle, and you're going to have an instruction moving around your pipeline every cycle. So you know, next PC again is going to update the PC. Do that based on the best information that you have at the time, which means generally +1, right? +1 instruction. So everything else should be the same, I believe. So try that. See what issues you run into. See how it goes. Think about how to resolve any issues. Go. So reset your machines. It seems like everyone has sort of executed enough to get a feel for what's happening here. What are some of the issues we ran into? I think just about everybody brought this up with me already, at least one issue. Ooh, you guys are in earshot, so. 2 issues? Okay, so you got through 2 iterations. Okay, good. And did you run into any issues? Right. So you're executing along, I forget which one of these is a branch. This one's a branch, probably, right? So you get down to 6, you know, everything's going sequentially. You get down to 6. This is being fetched. Then you pass that along. This is being decoded and register file access. This one's being fetched. Then you shift again. This one's being fetched. This one's being decoded. And this one's being executed. At that point, you figure out your branching. You've already fetched this. You've already fetched this. These are on what would be called the bad path. Okay, these should not be executed. So how do you deal with that? And that's what we'll look at next. So that's one issue. That would be referred to as a control hazard. Anybody come across any other issues? Right. So register read is happening with instruction decode. That's the 2nd stage. Register write is happening in the 4th stage. So I forget which instructions are set up this way. But if you have one instruction writing the register file, the next instruction reading the register file, you're trying to read it before the register's been written. So you get the old value, just as he said. So that's a read after write hazard. Okay, so these sorts of scenarios that depend on the sequencing of operations are referred to as hazards. And when we try to pipeline our CPU and hardware, just as we tried to pipeline ourselves as the CPU, these are the issues we're going to run into. These are the issues we have to find a resolution for. So one more thought I had overnight, actually, for one more exercise we can do with this. Instead of each of you being a stage in the pipeline, now let's have each of you be an instruction in the pipeline. Okay, so you will perform every stage of execution of the instruction. One person will fetch an instruction. You can push your chairs aside, stand around the table, right? Fetch an instruction from the instruction memory. Update the PC, fetch an instruction, then march around the table to the next stage. Right, so fetch stage, grab the instruction, decode it. So again, now that you need to execute all, or to perform all of these stages, I'll walk through them again. When you decode and access the register file, you're flipping the card over, determining what the instruction is, looking at the values in the register file, determining what those values are. Then you hand off to execute, which is no longer a handoff, it's you, you're the instruction. So walk around to the execute stage, do the mental execution on those values, come up with the result, clock, so step around to the next, write the result back to the register file, and then become the next instruction, right? So we'll actually physically walk around the table, be the instruction, keep executing, and see what happens, right? Behavior should be the same, but this will give you new perspective as the instruction instead of the stage. Okay, so we'll just do that for 5 minutes, and then we'll continue on and start looking at the hardware model. Push the chairs aside, make yourself space. Don't want any injuries. Everybody should be standing. So maybe at this point it would be good to try to resolve these hazards, right? So does anybody have any suggestions for strategies to resolve the branch hazard, the control hazard? Any suggestion for how to resolve the branch hazard? So try to do the decode earlier so that you can detect the branch earlier. So I'm going to assume that it's not feasible to do that. An idle cycle, so how are you generating that idle cycle? Between every instruction or just for branches? Yeah, so how do you detect that idle cycle? Or, you know, when do you know there's an idle cycle? Yeah. Yeah. Mm-hmm. Mm-hmm. Right, so we can use what's called branch prediction to reduce the likelihood of trouble. We can, early in the pipeline, predict, hey, I've seen this instruction before. This is a branch. It's been taken before. Let me take it quickly before I run into trouble. So that's going to help with our performance, but it's not going to help with correctness, right? So let's worry about correctness first. how are we going to make sure that we're not executing instructions that we shouldn't execute? Okay, so we know, let's figure out what we know, right? We have a branch instruction, and I'll go back to this one. So this one's a branch, right? So we fetched this one. We continue on, we fetch this one, we fetch this one. At this point, we're executing the branch. At this point, we know it's a branch. We know it should be taken. We know we messed up, right? This one's still, this one's being decoded and accessing the register file. This one's being fetched. What do we do? Well, neither of these instructions has caused any harm yet. None of them has updated state. This is just decoded. It's read values from the register file. This one just fetched. Nothing's happened yet. They're bad. So squash them. Okay, let them go through the pipe, but make sure they don't commit any of their results. And then you update the PC and everything is fine. All right, you just need to make sure you're cleaning up these guys and marking them as bad path, don't do anything. So that's sufficient to resolve the hazard. And then, as Professor Bopu said, you can go a step further and try to improve the performance to avoid these bubbles by making predictions about the branch and about its target, so that you know, if you predict correctly and quickly, potentially you could have this instruction be the correct one and actually, you know, fetch this one or that one, whatever it is. All right, so what about the other condition, the read after write? So whichever the two instructions are, say this one is a write and this one is reading the same index. You don't have time to do the register file write and register file read, right? That's 2 cycles apart. What do we do? Forwarding? Yeah, so you know, unless you want to do something more catastrophic like flush the whole pipeline, assuming we want reasonable performance, that's a condition you have to detect and have a special case for, right? So this guy writes, this guy reads, you decoded the registers. Well, let's do this in sequence. So this guy would be the write operation, and maybe he's in his decode register file read. This guy's being fetched. Next clock stage, this guy is being decoded. This guy is being executed. At that point, when you're decoding, right, you have to detect the read after write. So you're doing comparisons of this guy's registers and this guy's registers, and you're saying, hey, this guy's source registers are the same one that this guy wrote. So instead of sending the data through the register file, we have to add this forwarding path for the one instruction to forward that value to the other. So, you know, that involves more muxing of the data, can be delay. This can be a very critical path, but we try to, you know, optimize that path and make that work so that we don't have to squash instructions in the pipeline and take more drastic action, right? And so those are the things that we'll look at in more detail in the hardware logic. All right. So let's turn to hardware. Let's talk about these things with the War5 CPU. It's got some pictures we can talk to. So let me open up War5. You can, you know, clean up your desk space. We're done with the cards for now. So here's the CPU that you guys were just emulating. It's got 4 stages. You've got the PC update and fetch. Right. Decode and register file read. arithmetic logic unit, register file write. Right, so this is the exercise we just did. We're running the same test program, or at least a program that's very similar. So first stepping past reset here. So what we're looking at here is referred to as a waterfall diagram. This is showing us what stage each instruction is in at a given time. So if I look at a vertical column here, that's going to tell me that the OR I instruction at this time, right, time is left to right. So at this time, the OR I instruction is in its fetch stage. Then time progresses, OR I goes to its decode register file read, and this next OR I is fetched. Okay, we step the clock, everything shifts, OR I progresses down the pipeline, this OR I progresses down the pipeline, this OR I gets fetched, right? So this is our view of the instructions over time. Each instruction is going to march through the pipeline, each instruction a cycle after the one before. As we step simulation forward, these, the green here is indicating the register forwarding, so the read after write, and the blue down here is our control hazard, the branch. Okay. So let's look at the branch first, I guess. So here's our BLT. We had two instructions behind it. In this particular implementation, I'm assuming a two-cycle branch penalty, meaning we know the branch and its target in time to redirect this instruction, but not the ones before it. So the ones before it, as we said, we have to squash those, make sure they don't commit any results. And that's represented as the gray here. The register dependencies. Right here we have an add I instruction that's producing, let me see if I have a one cycle. I think all I have here are two cycle dependencies. Okay, here's a one cycle. So this instruction is producing a result in A0. This store instruction is reading A0. Okay, so read after write. A0 happens to be X10. That's what we're showing here. That same register is used as the second source register. Okay, so there's a register dependency. This first instruction knows the register value after it's read from, I should know it earlier. So the assumptions are slightly different with this one. There's an extra cycle of delay. But the assumption here is that, actually let me look at my stages. ALU, okay. So this first instruction has produced the result for its destination register after execution, which is at the end of this, this blue stage, right? This is the execution stage. So here we have the result that's needed by the next instruction. It needs that result to feed into its execution, right? So you have a loop from the ALU back to the input of the ALU the next cycle for the next instruction. So this is the bypass path, forwarding that result from the first instruction to the instruction behind it. Here, I'm assuming we actually have two cycles of register bypass. So I'm assuming that we don't have time to write the register file and then read the register file for instructions that are two cycles apart as well. And so you see the same sort of bypass for this OR I instruction that's also producing a result in A0. This line here actually is not utilized because we're also writing A0 in this instruction. Any questions about those? Okay, so now we're going to progress through our hardware. We're going to take incremental steps to get to this point, but this is essentially where we're going to land. All right. This one? Yeah, so the assumption here, and I don't, our assumption will be different, but this longer path, a two-cycle path, is one instruction's ALU produces a result, writes that result to the register file. We need to read that out of the register file and loop it back. You know, that would be a two-cycle loop. I'm assuming here that we do not have time to do that two-cycle loop, so this design is adding a bypass path for that as well. Right. You know, it's a close call, right? The register file write could take the entire cycle, and then that's right. Yeah. Okay, so let's look at our CPU diagram. This is what we currently have. We just looked at the waterfall diagram. This is what I refer to as a waterfall logic diagram. I've actually never seen anyone draw these this way, but I think they're very helpful. So I'm just representing the logic that is seen by each instruction that goes through the pipeline. So we're looking at, you know, a copy of our whole pipeline for each instruction. So for two instructions back to back with our current CPU, this is how we would represent their execution, right? The first instruction is going through these stages. The second instruction is going through those same stages a little bit later. And then on this diagram, we can represent where information from the first instruction is passed to the second instruction. So when we're just looking at a single, when we're looking at the logic itself and connecting up paths from one instruction to the next, those are loops from one clock stage back around, right? So the PC, for example, we compute the next PC, we do PC plus 1, that feeds back to the instruction behind us, and we draw it this way. In the waterfall logic diagram, I've represented the logic that's seen by each instruction separately, so that loopback path here is represented as a path feeding to the next instruction, right? So we can more clearly see what is viewed by each instruction or what relates to each instruction. And similarly, the register file read is coming from the register file as updated by the previous instruction through this path. So it's just a different way to look at the same information. To pipeline this, we want to introduce more stages, so more stage boundaries. So, you know, the first thing is just to reassign the pipe stage for our logic. When we do that, this becomes the waterfall diagram, right? The branch hazard is this first exclamation mark here. The branch of the first instruction, its target, its taken information is computed in stage 3, the execute stage. The next instruction needs that, okay? So this is a depiction of the branch hazard, the control hazard. The read after write is this other hazard. right? The register file write is being performed by the first instruction. The value that's written is not available to read until stage 4, and it's needed here in stage, why is that labeled 2? 2. Yeah, that's correct, okay. Is needed a cycle earlier in the next instructions, stage 2. So those are the conditions that we have to address. We can kind of view the logic this way, that what we need is this one cycle loop, but it's coming from 2 cycles later. This is implying anti-flip-flops. Until we invent an anti-flip-flop, we're going to have to come up with a different solution. The waterfall diagram we looked at with warp 5, but again here we have a destination register of 3, a source register of 3, and the hazard and the branch hazard producing a destination here, a target rather, and then needing that target here. So just different ways of looking at the same hazards. So as I said, we're going to take incremental steps to work toward a solution. The first incremental step will be to stretch our logic out in a pipeline, but not take advantage of the fact that we have the pipeline, and just do one instruction every 3rd cycle. So we'll have the logic, pipelined out and taking multiple cycles to execute, but we're still going to essentially have the same throughput, one instruction every 3rd clock cycle, right? So maybe we speed up the clock by a factor of 3, but we're still only executing the instructions with similar latency. Knowing that we don't have valid instructions between these, we have no hazards. There's no instruction to create that hazard, right? So this is the approach that we will take first. Here's the waterfall logic diagram for that, right? We know that these are 3 cycles apart, so we have time. So to implement this, first we need to know which instructions are valid and which are invalid, right? Which are the grays. So we'll generate for ourselves a valid signal. We can do that just by marching valid through the pipeline and kind of looping it back, right? So after reset, we'll generate the first valid instruction, and then so here's our reset, right? We'll generate ourselves a start pulse to kick things off. After we generate that start pulse, the valid is just the valid from 3 cycles ago. Okay. So, if we have a start pulse or we have a valid 3 cycles ago, we're valid. Okay, so we'll do this in 2 steps. First is to generate the start pulse. So that's going to be an edge detect. That's similar to what we did for the calculator button, right? And the next is to generate valid, which again, we pulse valid if we pulsed start or if we pulsed valid 3 cycles ago. Any questions? All right, so hopefully you have your code from yesterday and you can add this to it. One more thing I should clarify. So just so it's clear, at this point, all of our logic is still the same as before. It's all in stage 1, right? We haven't stretched our logic out in the pipeline, but we're prepping to do that, right? So we're creating the gap between instructions. So we still have all our logic in stage 1, but we're creating these 2 dead cycles, and then creating the valid, which we will soon use to control whether we're going to execute an instruction or not. So again, incremental. First, we're going to stretch the pipeline empty. Later, we'll actually distribute the logic. But as we know with TL Verilog, distributing the logic is a safe operation. Logically, it doesn't matter how the logic is distributed. For now, it's all still in stage one. So at this point, you're just creating the logic to create the valid that pulses every third cycle. It's not even hooked up. So the rest of it is your original. Okay, so we want this start signal to pulse after reset. Start is not reset. Previously, we had reset. So that's our edge detect. And then valid. We want to make sure valid is 0 during reset. We don't want any spurious activity on valid to generate more pulses later. So reset to 0. Otherwise, we want to use, we want to pulse on start, and we also want to pulse on, based on previous valid pulses 3 cycles ago. Okay, so we want to pick up this pulse, and then for the next pulses, we want to pick up the pulse from 3 cycles ago. Okay, so now that we have a valid signal, we're introducing a new concept that our core was not aware of before, this concept of valid instructions. We want to make sure that an instruction that's not valid does not commit any architectural state, right? It doesn't matter what an invalid instruction happens to do in the hardware, what the hardware thinks that instruction is, as long as we cut off the impact that it has on state. State in our design is the program counter and the register file. Okay, all the instructions that we are supporting right now are only operating out of the register file. That's what their instruction's responsible for, is operating on registers, updating registers. So the register file is currently defining the state of our machine. And then the program counter as well as the state of our machine, right? When you guys were human CPUs, those were the two things that were updated. So as long as we avoid any impact to those states from invalid instructions, we don't care how the machine's interpreting the instructions. So we're going to add the logic to support that, to support this notion of an invalid instruction and prevent any updates. So first we'll look at the register file. So you want to make sure that if the instruction is invalid, as indicated by this new signal, valid, that we created, make sure we're not doing any register file writes. And then the PC. We want to make sure that we're not updating the PC for invalid instructions. Where's that in my instructions? Okay. So the way I've done that is to not care what the PC is for the invalids and just update the PC as +1 in a 3-cycle loop that matches the 3-cycle cadence that we have, right? So the PC increment, instead of applying that with a 1-cycle loop, we'll apply that with a 3-cycle loop. So we'll use incremented PC ahead by 3 instead of ahead by 1. And then similarly, the update for a branch, it's not from the last instruction now, it's from the instruction 3 cycles ago. So the branch target calculation now also will come out of stage 3 and back to the PC. Okay, so this is helping us free up extra cycles, which now are empty, but once we free them up, we can stretch our logic out. Since we now have the concept of invalid instructions, we also need to factor validity into take and branch. We don't want to update the PC for branches that are not valid. So we only want to do the PC update if we have a take and branch that's valid. Any questions about those steps or why we're doing them? Yeah. Just repeat. Yeah, so we want to make sure we've introduced this new concept of invalid instructions. We want to make sure the invalid instructions do no harm. So we need to cut off the write to the register file for invalid instructions. And then for the PC update, we're updating on a 3-cycle cadence. So we'll manage the PC update just every 3rd instruction instead of every instruction. So the PC gets updated by the instruction 3 cycles ago. We know that's the one that was valid. So the increment, PC increment, loops around with 3 cycles, and the branch, the update for branch instructions. Now that update should be for valid branch instructions, and that's going to be a 3-cycle loop as well. So the instruction that's 3 ahead of us is the one that updates the PC. Okay. Okay, so I think most of you are done. I'll start walking through it myself while you finish up. So step 1 here is preventing the register file write for invalid instructions. You can express that a couple different ways, but the way I've done it is to and valid with the entire expression here, right? If we're not valid, we want this to be 0. Step 2 is avoiding the redirect for the PC for invalid branches. So taken branch. Again, we want that to be 0 if we're not valid. Again, you can code that various ways. I'll do it this way. So if we're not valid, then taken branch is 0. And I want to call that now valid taken branch. This is now valid taken branch. And then I want to affect my PC update from the instruction 3 cycles ago instead of the one last cycle. So I'm going to change this to 3. And the value is also circulating around 3 times. And the PC, incremented PC from 3 cycles ago. So that's what's depicted here in red. Right, so again, this is ensuring that the thing that updates the PC is the instruction 3 cycles ago, not the previous. So this is the picture that we're implementing, right? So the PC update, this instruction should be based on the PC update from this instruction 3 cycles ago. Or, in other words, ahead of us in the pipeline by 3 stages. So let me compile. And what we should see in visualization now, step 1 at a time. We see all these gray instructions. Those are invalid. And we have our first valid instruction. We have 2 cycles of invalid instructions. And then the next instruction. Everything looks good. Let's make sure we're branching correctly here. That's right. Okay, so just to review, make sure everybody caught everything. The first change was here. Register write enable. That was step 1. Step 2, valid taken branch. Factoring valid into the branch. Not sure actually if we need taken branch to still exist. Just to be safe, since my slides keep taken branch as a separate signal, let's code it that way. So let's do taken branch is valid and taken branch. And we'll revert this. So valid taken branch is the second one, and then the third one is all these updates to the PC mux up here. Looks like everybody's good. So now that we have our 3-cycle cadence set up, we no longer have any dependencies from one cycle to the next. All of our dependency loops are 3 cycles. Now we can stretch out our logic without breaking anything. You can. Yeah. You'll never read an invalid instruction, but you'll keep reading the same instruction, right? So if you keep reading the same instruction, which was a branch, now you're executing that branch multiple times. Maybe that's okay. Still kind of risky. Philosophically, right, you just want to say, this guy's invalid, let him do whatever he wants to do. But make sure he doesn't update any state. Now, so the approach we took with that, right, the machine's still doing stuff. That's still burning power. So it might still be valuable to kind of cut off the instruction early on and make sure we're not burning power for invalids. But at this point, it's sort of an intermediate step to transform our design to what we want it to be. So at this point, we're more focused on correct functionality. So this step is where we actually pipeline the CPU, okay? So this is the step that, if you were using RTL, would represent half of the workshop. For us, it's going to be 5 minutes. So we're just taking the logic and rebucketing to different pipeline stages. So that's, let's see, stage is cut and paste. So that's step one, is to partition the logic as depicted here. Also, to support this change, some of our code is in macros, so we need to tell the macros to change their timing as well. We need to update the register file to use at2 and at3 to say read in stage 2, write in stage, read in, yeah, actually read in stage 2, write in stage 3, begin the write in stage 3. Yeah, I mean, the parenthetical note doesn't really matter, right? Functionally, so making this change does change kind of the functionality of read and write, right? Previously, the read and write were happening at the same stage. Now we've stretched it out, which can have the functional impact that we discussed, where you know, we have a read after write hazard because we've separated those operations into separate stages. Since we don't have back-to-back instructions at this point, it's okay. That's why we're not doing instructions back-to-back. But just to note that this change is potentially a functional change. Okay, and that's it. So it's just those two steps, right? Distributing your logic and then changing the parameters to the register file. So how should we address these hazards so that we can execute instructions back to back? So let's first look at the red line here. So this is okay. So we're dealing with the register file bypass first, or register forwarding. So the register file is producing a result at the beginning of stage 4 for the instruction 2 cycles away, 2 cycles behind. We can access that value in time to write the register file. Right. So this is the path that when I showed the warp 5 waterfall diagram and the hazards there, in that design, I was assuming this path was too tight and I couldn't meet it. We're going to assume that we can meet this path, but the path from back-to-back instructions we can't meet. So for that, the register file would be producing a value here that we need here. So what we need to do is, instead of getting that value out of the register file, we need to bypass it. So we need to instead, in blue, grab the value from the ALU and forward that to the next instruction, to its ALU execution. Okay. So we need a multiplexer. The multiplexer on each source operand needs to be controlled by whether that source operand has the same index as a valid result produced by the previous instruction. Okay, so if this instruction's result is in the same register as this instruction's source, we need to use this, this value. Okay, so this path through the register file is fine. This path is broken. We'll fix this broken path with this forwarding path. We were just looking at the waterfall logic diagram. If we just look at the logic diagram, right, that forwarding path is a path that loops around from stage 3 back to stage 2. So, and ahead by reference, right? We're referencing the second instruction is referencing its previous instruction. Okay, is that picture clear? So to implement this, so 1 is nothing. It's already good. So step 2 is to update the expression for the source value, right? The value feeding into the ALU. We need that value to support this bypass path. So we want to select the previous result if it was written to the register file, so the write was enabled for it, and it was the same index, previous RD was the same index as my index. All right, for both source registers. Let's see. And then third is just a note, right? If you follow these instructions literally, this is fine, but I actually had a bug in the first version of this course where the values here feeding into the branch comparison were before the MUX instead of after the MUX. This calculation has to consider the bypassed registers as well to make sure that this branches comparison are based on the right register values. So just make sure that your comparison logic is based on these signal names, not the signals coming straight out of the register file. Okay. So after this, we will break for lunch.